Hey everyone, I'm so sorry that we are running a bit late. We are going to do our best to make up some time here. So we'll go ahead and get started. I will share my screen. All right, welcome to the second installment of the Simulation Showcase series. This is the Case Studies in Energy Efficiency edition, and this is presented by the IBPSA-USA EPSI committee. My name is Kate, and I'll be your moderator for today. And I assume that everybody's already settled in since we're running a little bit late, but I'll give you a quick rundown of what to expect. We are recording this session and it'll be available on the IBPSA USA YouTube channel. If you missed last month's simulation showcase, you can watch the recording on YouTube now. If you have any issues hearing the presentation, please try calling in by phone instead of using computer audio. You can participate by posting questions and comments in the Q&A tab at the bottom of your screen. Questions will be viewable by all attendees, and there is an option to submit anonymously if you prefer. I'll relay your questions live to each of the presenters following the presentation. For those of you who don't know us, we are EPSI, which stands for the Emerging Professionals and Students of IBPSA USA. EPSI is a peer group under IBPSA USA focused on professionals with less than 5 years of experience in the building performance industry. We connect early career analysts with resources, networking opportunities, and leadership insights to help you grow your career. We're always looking for more energy enthusiasts to join, so please scan the QR code to join our community. This is the second installment of our new webinar series, Simulation Showcase. The series highlights the work of emerging professionals and students using building simulation to tackle challenges like energy efficiency, decarbonization, and indoor environmental quality. We invited students and early career professionals to submit their simulation-based projects. The selected participants will now present a 10 to 15-minute spotlight session and followed by audience Q&A. And then our reviewers will assign scores based on their review criteria. The 3 finalists will be recognized at SimBuild 2026 in Minneapolis. Today's session is the second in this monthly series running through February, and presenters today will talk about how simulation helped develop real-world design solutions. Without further ado, I'd like to introduce our first speaker. So our first speaker is Anuradha Kadam. She is a sustainability consultant with Arup, specializing in building performance analysis, decarbonization, and energy efficiency. She has a B.Arch from NJIT, an MS.Arch in high performance buildings from Georgia Tech, and has experience in decarbonization planning, energy modeling across warehouses, healthcare, and office projects, and solar feasibility and financial analysis. Her research on low-budget weatherization retrofits for disadvantaged communities is published in Energy and Buildings, and she continues to focus on equitable decarbonization and sustainability standards for affordable housing. Anuradha's interests include data visualization, whole building lifecycle assessment, and expanding accessibility and sustainability education. And she is currently teaching sustainable architecture at NJIT and is currently supporting the IBPSA USA's New York Metropolitan chapter. As a reminder, please post your questions during the presentation and I'll relay them to our speaker following their presentation. All yours, Anuradha.
Okay, everyone see my screen? Great. Hi, my name is Anuradha Kadam, and today I am excited to share with you all a case study on decarbonizing a portfolio of plasma donation centers. Okay. First, I want to acknowledge this incredible team of decarbonization experts at Arup. Each person on this team played a significant role in putting together the decarbonization roadmap that I'm about to present to you all. My role on this team was primarily as the energy modeler, which is why I'll use this time to focus on building simulations, methodology, and analysis that contributed to the final roadmap for our client. So the client is following the Science-Based Targets Initiative, in which the first target is a 65% reduction in emissions from a 2016 baseline by 2030. The final target is net zero emissions with a 10% margin of error by 2035. This building portfolio of plasma donation centers consists of 2 prototype geometries, a standalone and a strip mall. There is about an even amount of each geometry, with a total of over 200 existing buildings located across climate zones 2 through 5 and all throughout the United States. The differences in geometry, such as window-to-wall ratio and program areas, impacts energy use and energy reduction from retrofits. So you can see some of the differences in the two prototype designs here. The standalone prototype has a larger total EUI than the strip mall. We know this is a result of geometry and program area differences because these models consisted of the same exact programs, internal gains, schedules, envelope constructions, heating, ventilation, hot water, and most other inputs. Some of the rooms that are specific to plasma donation centers are the waiting room, donation room, exam room, and the freezers, which kind of vary in size between the two designs. These programs have very similar base load EUI for lighting, refrigeration, and plug loads. The biggest difference in EUI is for hot water use, which is significantly greater in the standalone model compared to the strip mall. The standalone also has slightly greater space heating, cooling, and central fan use than the strip mall. And so the key takeaway here is that for plasma donation centers, hot water uses more energy than space heating, which is somewhat atypical for most building types. When you look at the 2023 emissions breakdown, you can see that the majority of emissions are from electricity. However, in 2022, a virtual power purchase agreement, or VPPA, was signed, which essentially offsets all Scope 2 emissions for this building portfolio. This is a significant context that informs the final recommendations for this decarbonization roadmap because the priority is reduction of Scope 1 emissions from refrigerants and natural gas use. So this business as usual emissions forecast estimates future portfolio emissions from 2025 to 2035, accounting for portfolio growth. The roadmap assumes 5 new all-electric strip mall plasma donation centers added each year across climate zones 2 through 5. This forecast assumes that annual emissions from existing sites are remaining the same and does not account for any grid decarbonization. It also assumes that new sites will be using low GWP refrigerants and will leak at a similar rate to existing buildings. So the simulation exercise for developing the decarbonization roadmap uses a iterative process and approach to simulation and analysis to reach the final recommendation. So step one here investigates a long list of emission reduction measures, or ERMs, um, independently to determine impact in each climate zone and for each prototype. Next, the results of this set of simulations are analyzed for impact on energy reduction and prioritized by cost implication. In step three, the ERMs are bundled into several options that are tested again across all climate zones and prototypes. The analysis identifies combinations with the highest impact on Scope 1 emissions reduction and also considers cost implications of each bundle. Finally, in step 5, all analyses, including measures that are hand calculated rather than energy modeled, are evaluated to develop a final recommendation. In our long list of ERMs, we have refrigerant management, which is not energy modeled, but actually calculated separately. The energy efficiency measures primarily relate to building envelope and demand reduction, along with submetering, which is not modeled. Next, we have fuel switching measures that convert to high efficiency electric resistance for lower cost options and air source heat pumps for high efficiency as well. And finally, we consider on-site renewable energy generation in the form of rooftop or carport solar and battery storage. As you might be imagining by now, consideration of 2 prototypes, 2 fuel sources, 5 climate zones, about 9 ERMs, and about 2 iterations results in over 200 different simulations. So this simulation exercise uses IESVE for all of its energy modeling. And we decided to use its relatively new parametric simulation option to quickly simulate every single design option, which also now allows for somewhat of a sensitivity analysis for these 2 prototypes. This helped us efficiently and identify low cost and high impact ERMs. The parametric simulation provided results in the form of these parallel coordinate charts pictured here, which is an interactive and intuitive method to identifying the design options with the lowest EUI across climate zones. These EUIs are also broken down by electricity and natural gas, which we decided to further process into graphs and heat map tables for analysis. For analysis, I wanted to first share the energy efficiency measures results. Air sealing here is a clear winner among all climate zones with both building all climate zones and both building typologies, with the largest reduction in both electric and gas EUI. Then in these heat map tables, we can compare percent reduction in EUI from the business as usual case across climate zones and ERMs. This heat map table also considers upfront costs all the way at the top, and most of these measures end up not really resulting in enough reduction in scope 1 emissions to be worth the upfront cost, with the exception of air sealing. Next, looking at fuel switching results, the R2 electrification has a smaller impact on scope 1 emissions than the reheat system. Electrifying hot water instead seems to reduce scope 1 emissions the most, which aligns with our understanding that hot water use is actually larger than space heating for this building typology. Looking at the heat map tables and including cost considerations, we can see that air source heat pump hot water system has twice as much energy savings as an electric resistance system. However, it also costs 3 times as much as the electric resistance system. So our rigorous analysis increased confidence in the results for our client, who ultimately agreed to take the burden of upfront costs of fuel switching all heating and hot water systems to high efficiency electric systems in order to meet the SBTI and net zero sustainability targets. The low cost option of no fuel switching is also considered for comparison, but it's unideal and definitely won't meet this SBTI target. At this point, rooftop solar was also deprioritized since it doesn't reduce any scope 1 emissions at all. The result of these bundles compared against gas or electric business as usual fuel sources are presented here. The all-electric prototypes only included air sealing because they're already electric, which explains why gas-fueled building retrofits have or gas-fueled glass-sourced building retrofits have a much higher emissions reduction rate than all-electric buildings. Since energy modeled ERMs ended up having a limited ability to reduce scope 1 emissions, especially for the all electric buildings, refrigerant management ended up being the most significant and high priority ERM for this roadmap. The recommended option for refrigerants includes converting freezers at the end of useful life to ultra low GWP refrigerants, as well as using ultra low GWP refrigerants for all the new construction buildings. Next, the recommendation also includes converting all other existing freezers and HVAC to low GWP refrigerants. At the end, our phased approach to decarbonizing this portfolio of buildings ends up resulting in meeting the 2030 emissions reduction with a 74% reduction from 2016 baseline, which is actually better than the target. By 2035, the projected emissions are a 92% reduction from the 2016 baseline, which is within the 10% margin of error for net zero energy, proving the success of this recommended roadmap. Thank you.
Thank you so much for that great presentation. Well, I'd love to get some questions going in the chat, and I'll start us off with one now. What is the status of this project currently?
So this project was delivered to our client maybe about a year ago. So I think it's in hopefully likely in the implementation phase, but as consultants, we had to like hand off this project and I think we'd have to kind of check in with our client to see what's going on now.
Got it. And is there anything that you would do differently for the next project based on what you've learned for this one?
Hmm. Differently. There are a lot of moving pieces for this. I think we ended up, yeah, I can't think of anything exactly right now because we ended up doing so many like parts and pieces of the project that ended up being important, even though like the VPPA kind of made refrigerants a lot more important at the end of the day. Like I think this rigorous energy modeling exercise was really important for the client and like kind of really showing um, the state of the portfolio and like how best to decarbonize it. And also something that's not included in this presentation is like operational costs and utility data costs. And that was like heavily informed by the simulations that we did.
Got it. Yeah, it makes a lot of sense. Well, thanks so much. I'll try to get any questions to you that we get later on in the presentation in our presentations afterwards. So let's go ahead and move on to our next presenter. Ahmed Fez Khan is a Building Performance Consultant 1 at Affiliated Engineers, Inc., AEI, specializing in building performance modeling with Energy Plus, green building rating systems, water modeling, and data-driven analysis to support energy efficiency and carbon reduction strategies. He holds an MS in Civil Engineering and Building Performance from the University of Cincinnati and is a lead Green AP with experience applying ASHRAE 90.1, IECC, and LEED frameworks in both new construction and existing building projects. His recent work includes early stage energy modeling, code compliance analysis, refrigerant emissions evaluation, and utility data analysis to inform design decisions. His current project focuses on comparative analysis of energy conservation measures for a higher education laboratory facility, where he led modeling efforts and developed a rapid scenario evaluation tool to guide cost-effective decarbonization-focused design. All right, take it away. We can see your screen, but you are muted.
Okay. Okay. Thanks, Kate.
Yep.
Hello, everyone.
Okay, we can hear you.
Yep, thanks. One second. Hello, everyone. My name is Ahmed Faiz Khan, and I'm a Building Performance Consultant 1 at Affiliated Engineers, or AEI, in its Madison office. And the title of my case study is Cost-Effective Energy Conservation Measures in a Higher Education Teaching Lab Facility. First, I'll give a project background. So this project was around close to 68,000 square feet higher education teaching lab facility in the US state of Tennessee. This project is located in ASHRAE Climate Zone 3A with a window to wall ratio around 4%. And this project had several different space types. For example, there was different office spaces, classroom spaces, and dry labs and wet labs, among other spaces. Since this project had pretty tight cost constraints, so the project goals were to meet the cost constraints from the owner and meeting minimum energy code requirements of ASHRAE 90.1 2016 in the state of Tennessee. So in this case study, I evaluated several energy conservation measures, or ECMs, to meet these goals in the schematic design, or SD phase. So I'll talk about the approach that I used. So using Energy Plus simulation, I evaluated several ECMs based on their first cost, which includes material plus installation cost and operational energy cost. The ECMs that I evaluated, they were related to envelope parameters, airside HVAC measures, different cooling options, different types of lab fume hoods, and lab fan exhaust control. The design team then recommended some of the ECMs to the project owner. Now I'll talk about the specific ECMs that I analyzed. So in terms of envelope parameters, I evaluated different variations of wall insulation and roof insulation, and also different glazing options. In terms of airside HVAC measures, I evaluated the options of with and without energy recovery via runaround loop, and also the options of with and without airside economizer with fixed variable temperature. For cooling options, I evaluated DX cooling with different efficiencies, and also air-cooled chillers with different full load and part load efficiencies. As I mentioned, there were several wet labs in this project. So in the last category of ECMs, I evaluated different types of lab fume hoods, for example, manual sash fume hoods and auto sash fume hoods, and also wind responsive fan exhaust control. I'll give a brief overview of these ECMs. So fume hoods are ventilated enclosures that are used to protect the lab occupants from hazardous chemicals. And in manual sash fume hoods, the user need to open and close the sash manually by hand. And as a result, there could be like a significant energy waste from this, because if the user forgets to close the sash, it could be open and otherwise. But on the other hand, in auto sash fume hoods, the motion sensors detect automatically when the user approaches, the sash gets opened and it gets closed when the user walks away. So these auto sash fume hoods, they could provide significant fan energy savings compared to manual sash fume hoods. So I evaluated these both of these fume hoods. And in terms of wind responsive fan exhaust control, in this technique, anemometers they installed at the rooftop, and they measure wind speed and wind direction, and a variable frequency drives or VFDs. Then they adjust the speed and direction of the exhaust air that are being exhausted from the lab. In this slide, I'm gonna talk about how the ECMs were evaluated. So for each of the ECM, as I mentioned, the annual operational energy cost was reviewed with first cost. First cost includes material plus installation cost, and then the design team recommended the options that were optimizing the savings to the owner. Then the owner reviewed those options and they selected some of the options that were recommended by the design team. And for some other ECMs, they focused mainly on first cost, and they selected the options that had the lowest first cost. So here in this chart grade, I have shown the variation of annual operational energy cost with first cost for all the variations of each ECM. And I've highlighted the ECMs that were recommended by the design team with yellow. Green is showing the ECMs that were not recommended by the design team but selected by the owner. While blue is showing the ECMs that were recommended by the design team and also selected by the owner. I'll also add that these ECMs, they were not evaluated just as individual measures. As you can see in the bottom right chart, I've shown the same variation, variation or the variation of same variables for all of the ECMs together as a whole. Before moving on to the next slide, I'll rephrase this slide by saying that some of the options, they were aligned with the owner selection, but others were not, because the owners the owner had preference for the lowest first cost, which is not bad from their perspective, as they had pretty tight cost constraints for the project. Now I'll talk about the savings based on whole building perspective. So the left chart is showing the variation of EUI, energy use intensity, in kBTU per square feet per year for the three cases. First case is for Asher 90.1 2016 baseline. The second case is the proposed ECMs that were selected by the owner. And the third case is showing the options that are recommended by the design team. The right chart is showing the variation of annual energy cost for the same three cases that I mentioned. And if you see, you can see that in terms of second option, so the second option, it has significant energy savings, significant EUI savings, and annual energy cost savings compared to the baseline, but it's not a lot, right? So if you compare the second option with the third option that was recommended by the design team, there could be some more savings. Quantitatively, if the owner selected the third option, it could be around 23% EUI savings and around 24% energy cost savings each year. For the third option, if the owner selected the third option over the second option. And obviously this would come with an additional investment of around $264,000, which could lead to around close to 6 years simple payback period, which is not bad. So I would say the owner selection had significant savings, but it is not optimal. Lessons learned. First, using simulation tools and with rough initial estimates of each ECM, we have a great potential in evaluating those ECMs in early stages of design. Second, simulation tools can provide great insights to stakeholders in finalizing the decisions based on simple metrics, for example, simple payback period, especially when there are significant cost constraints in the project. Third, as we saw in this project, owners often focus on first cost while making decisions, but the selection of parameters can be optimized and some greater savings can be achieved even at the same cost in some cases. Here are some of the references that I used in this case study. Thank you all for your attention. Thank you.
Thank you so much. That was really insightful. I've got a question for you to kick us off. I'm curious if you did any like future, if you would like to do, or if you did for this project, any sort of like future projections of cost or natural gas, or if it was just from like the 1 year of the study.
For now, I just used the virtual energy rate for the current virtual energy rate and did not use any projection of energy cost.
Gotcha. Yeah, and similar question to the previous one. What's the status of this project right now?
So it's under design as well. It's I think it's late DDs right now.
Got it.
Yeah.
Well, exciting. Yeah, I hope it gets implemented the way that you've envisioned. Thank you so much.
Thanks.
I think we'll go ahead and move on for now to our last presenter. Yiwei Liu is a third-year Doctor of Design candidate at the Harvard Graduate School of Design, where her research focuses on building performance simulation, carbon-aware design strategies, and the role of thermal storage in good responsive architecture. Her work examines how buildings can shift energy use in response to real-time marginal emissions to reduce carbon intensity without compromising comfort or requiring major infrastructure changes. She holds an MS in Architectural Studies and Building Technology from MIT, where she developed a Monte Carlo-based design tool for early-stage life cycle assessment, and a bachelor's degree in Architecture and Mathematics from the University of Southern California. Her professional and research experience spans architectural practice, environmental performance analysis, and monitoring House Zero at the Harvard Center for Green Buildings and Cities. Her current work uses Energy Plus and large-scale building stock models to evaluate and validate demand management strategies for decarbonization of the grid. Take it away.
Hi, Kate, thank you so much for the great introduction. So hi, everyone. My name is Yiwei Liu, and today I'll be talking about our project on carbon reduction through optimized solar heat gain in windows, especially for the case study of Chicago residential buildings. So let's begin with our amazing research team. So this research team includes Jialiang Xiang, who graduated from Harvard with MDes, and Professor Holly Samuelson, who recently made the transition from Harvard to MIT. So our project are basically trying to test the impact of increasing solar heat gain coefficient in existing building retrofits. So the model, the base model we use for our study is this Unreal Redstock models, which provides over 550,000 building models to representing the 2018 building stock. This is the version from 2022 release. So it basically has all the building housing stock characteristics database and use physics-based computer modeling, and we just utilize their models to represent the building stock of Chicago. As we all know that buildings are working hard to decarbonize, and one of the strategies is to electrify all houses. With that being the case, we'll see more and more electricity loads on the grids, probably more than we are currently capable of. For smart buildings, there's many different ways of shifting the loads and using optimized control. But we're considering buildings who are not so smart. What if you don't have sophisticated controls? What can you do as passive strategies to help with this for upcoming electricity peak? So that's why we decided to study the properties of windows, because it's just every building has to have windows, and especially in residential buildings, people want large windows, and we want to see how that can impact the building. So we, in a cold climate like Chicago, it's easy to foresee that with all building getting electrified, more and more loads will be shifted towards the winter, because now you're all reliant on electricity for heating rather than other fossil fuel sources like natural gas. So that's why our first hypothesis states that we suspect that higher solar heat gain coefficient than typical best practice, or what's recommended by the building code on the south-facing windows, can reduce the overall emissions from heating and cooling. So with that being said, we simulated around 2,000 case from the Unreal Redstock model, focusing on the north-south oriented models for Chicago, which upgraded to heat pump with existing power source as backup. And we increased the south-facing window solar heat gain to 0.7, just to give you a reference how different that is from the ASHRAE standards. So the like during the study time, the ASHRAE standards recommendation for maximum solar heat gain coefficient for a climate like Chicago is 0.33. So we're basically doubling the amount of solar heat gain. And then, so the weather file we use are also projected future file to account for the future, because we're basically simulating for future scenario with all buildings electrified. We use the long run CANBE and long run marginal emission data for the emission case, again, also foreseeing that future trend. So the objective is to reduce the overall emissions in heating and cooling. So from the first study, what we've seen is that with the like over 2,000 buildings simulated, we see that in the quote unquote current building stock, so without the heat pump upgrade, just by simply replacing your window with higher solar heat gain, you can result in about 0.7% savings on average in emission. And then with the heat pump upgraded case, because the energy itself drastically decreased from the baseline case, you see about 0.3% reduction in emission. So there are some key characteristics to point out that, as you can see, the distribution, some buildings can be negatively impacted. In this case, it's less than like 2%. But then there's some buildings who can benefit a lot larger. Like if, for example, some buildings are over like 8% or 6%. Those buildings have common features such as large south face window, large southern window area, which makes sense because we're only modifying the south-facing window solar heat gain in this case study. And then we also see that if it has low initial solar heat gain to start with, you see most of the benefits. So with all these things applied, when we look at the buildings with a high potential of saving, you see about like 1.7% for the current building stock and 0.7% for the heat pump upgraded cases. So then we started considering this question a little further. So during multiple studies, you will see like when people test different window upgrades, they tend to match solar heat gain coefficient with U value that's kind of negatively correlated, meaning that when the window is more insulated, it tends to have lower solar heat gain coefficient. This is common because when you think about it, when you upgrade from double pane to triple pane or single pane to double pane, you're adding another pane of glass, which potentially would reduce that solar heat gain coefficient. And there's also low E coatings, all these different technologies that that tends to reduce the solar heat gain coefficient when you increase the U value, but it's not the case anymore with the current technology being developed. Like for example, like vacuum glass that doesn't necessarily have low solar heat gain coefficients. With that being said, we wanted to study like whether like instead of upgrading the U value alone, when it's paired with high solar heat gain coefficient, does that give us a better result than just simply improving the insulating value alone? So in this case, we simulated all red stock models for Chicago, which is a little less than 5,000 buildings. And then we did these series of studies. So first we run the baseline model, so no change to the model. And then we upgraded all model to have good insulated glass required by the ASHRAE building code. And then we slowly increased the solar heat gain coefficient case by case. So upgrade 1, we upgraded to the cold max, which is 0.33, then upgraded only south facing window to 0.7, and then all the windows to 0.7 solar heat gain coefficient. So the result, what we've seen here is you see definitely the most change from the insulation upgrade alone. So as you can see here, it results in about 3.8% savings. But what we also see is that it actually, even though some buildings can be negatively impacted by the increase in solar heat gain coefficient, you see on average, it has a little bit more benefits than just upgrading the insulation value alone. And then when we look at high potential buildings, which are buildings that had poor insulation to begin with and are also leaky, that's what the ACH represent. It's the air change rate. You can see that like we can achieve 5.2% emission saving simply by just replacing the window with high solar heat gain coefficient. This is the result for the 2018 building stock, which is supposed to represent close to what we have currently. And then if we upgrade all buildings to be electrified and have air source heat pump, what we see that a little bit less benefit percentage-wise, but again, similar trend. Most savings are from the insulation upgrade, but with the combination of solar heat gain coefficient, you see on average more benefits with a few buildings that's negatively impacted. And so again, similar trend when windows are already beginning with poor insulation and are leaky, with buildings that are leaky, you see like about 3.5% average emission reduction from increasing solar heat gain coefficient. So so that's why, so now I want to talk about some future work. So first, the climate scenario we used a rather moderate weather file. Extreme weather file may influence the retrofit benefits. That's just currently not accounted for this study. And then we also have just used one carbon emission metric. Different emission metrics might change our result. And then we focused on solar heat gain only for the retrofit scope, but then broader upgrades can be also evaluated later. And then again, we did not account for user behavior. So right now, there's no blinds or anything, but potentially in the winter when the sun is like lower and there could be potential glare issues, people might not leave the window open as much as we simulated. And then also we did not optimize for the solar heat gain coefficient. We just simply used a very high value to make the point that maybe we should reconsider how we design the design building in cold climates. And then also we did not account for urban context, like buildings shading each other. Lastly, we did not do parametric testing to see what kind of windows or different shading devices can impact the result. So in summary, improving the real values of windows reduce carbon emissions for nearly all existing building homes in Chicago, and then upgrade to higher solar heat gain coefficient can reduce the average emission even further in such cold climates. The increase in south-facing solar heat gain alone, it's more effective for buildings with large south-facing windows and lower initial solar heat gain coefficient to begin with. The combination of U values and solar heat gain upgrade is more effective when the buildings start with poorly insulated glass, lower solar heat gain coefficient, and also leaky. So the reduction in heating load is so basically why people set this maximum solar heat gain coefficient is because they are trying to reduce the cooling load for the summer, because currently all of our cooling demand relies only on electricity. What we are trying to say is, even though with the increased solar heat gain, you're increasing the cooling load a little bit, but it's also done in the seasons where solar power is more abundant, potentially like the emission factor is lower. So that's why like having a little bit increase in cooling demand can actually be offsetted by the decrease in heating demand, resulting in an overall carbon reduction. And then lastly is this strategy can be very beneficial for some buildings, but applying this needs to be more strategically considered, as we see that some buildings might be negatively impacted from this upgrade. So thank you so much for your attention. If you have any further questions, feel free to reach out to me by email. Here's my email. Thank you so much.
Thank you so much. Great job presenting. We do have one question for you from the chat. So have you considered the effects of thermal comfort when increasing the SHGC? For example, occupants sitting near the windows experiencing overheating, even if the air temperature is at the desired set point.
That's outside of the scope of the study alone, but it's definitely something we should consider when we talk about increasing the solar heat gain coefficient. Right now, because every space is conditioned, we're just looking at the conditioned temperature. So yes, there is a potential that occupants may not be comfortable because of this increased solar heat gain. Thank you for that comment.
Yeah, thank you. All right. Appreciate everybody's presentations. Everyone did such a great job. I'll share my screen one more time so we can talk about other IBPSA upcoming events, and then we can wrap up. So thank you so much to our presenters. We hope you enjoyed sharing your projects, and we're really glad that IBPSA-USA could give you this platform to showcase your work. Thank you so much to our audience as well, especially for the delay in getting started. Thank you for sticking around and supporting our emerging professionals and students along their career path. We've got a few more events coming up, so make sure you check out the IBPSA website for what's next. Here are some upcoming webinars, and then we've also got the IBPSA semi-annual meeting at the ASHRAE Winter Conference. I'll also point out that for SimBuild presentations, the call for presentations is open now through January 19th. Please subscribe to our YouTube channel so you can take a look at today's recording and explore other webinars as well. And that's all we have. Thank you so much for your time. Have a good rest of your day. Bye.